Okay, I think that was about 5 minutes. So let's get right into it, unless there's any questions that anybody wants to pose. All right, element of the day, phosphorus. Phosphorus is necessary for both you and plants to live. It is an essential element. Most of the phosphorus we use nowadays is lost to the sea. You dump phosphorus on plants to make them grow, and that's mixed in with the fertilizer. And then irrigation tends to make it slowly wash towards the ocean. And so it ends up there. Almost all of the easily available phosphorus we have in the world is in the Western Sahara, which is controlled by Morocco, and they're very mysterious about it. And there's a gigantic conveyor belt that goes from the Western Sahara into Morocco that carries the phosphorus. And Morocco is very tight-lipped about how much is in there and, you know, what their mining practices are and so on and so forth. So we don't really know when we're going to run out of phosphorus. We know we are at some point going to have difficulty with it. Animals pee out phosphorus. You know, animals eat the plants, which has the phosphorus, they get the phosphorus, and then it eventually gets eliminated from your body. I make a very strong prediction that before the end of your life, probably that phosphorus will be extracted before it enters a waste stream. Like, we're gonna need it. We're gonna need phosphorus. So that's what I know about phosphorus. There's a phosphorus crisis coming. Unit 3. This is going to be motion of astronomical bodies. So how do planets rotate around each other, so on and so forth. All the rules that we'll learn in this chapter can also be applied to stars and binary systems and so on and so forth. But we're going to focus on planets, and specifically on the planets that are in our solar system, since those are the ones we've known about the longest. Recent advances in telescopes have taught us that the universe is full of planets. There's just planets abounding everywhere. Most star systems seem to have planets. You know, 30 years ago, even 20 years ago, we did not know that for sure, but now we do. And I'll tell you about the techniques we use to find them in a later unit. We're also going to touch on calendars because I don't know where else to put them. So they got to go somewhere. The keeping of time by what's happening in the sky is pretty much the only convenient way to keep time. We typically go by how long it takes the Earth to go around the sun, although lots and lots of cultures also measure their time by moon cycles and what a lunar year is, and that works just fine. So, challenge problem, and I'm not gonna give you all 5 minutes to think about this and write it down, but I want you to at least think for 30 seconds. Why does the North Star change over time? Specifically, I want you to think about what is happening to the Earth over time to cause the star aligned with the North to shift. About how long does this take? And typically I would walk around the classroom and look at what people are writing and then give them some credit for it on the spot. But that's not going to happen here. So 30 seconds, then I'll ask if anybody feels like they want to chime in. And I'll do a repeat of the explanation that I gave you all about this earlier. Anybody feel like cudgeling their memory and talking about this?
I want to try. I think it's because the Earth is shifting a little bit, or rotating in a way. It's constantly rotating, but it's like shifting. And each so many centuries or years, the star is shifting also.
That is brilliant, and you are right. I'm going to be a little bit more specific about it. Have I just spotlighted the chalkboard? Like, is the chalkboard now filling your field of view? Great. So this is how the Earth goes around the sun. The Earth has a tilt relative to its orbital axis. So the orbital axis of the Earth is like this. It's a big wide circle, more or less aligned with all the rest of the circles that the planets in the solar system go around. And the Earth is inclined at about 23 degrees. 23.5 right now, I think. And it's definitely too small for you to see, but both these numbers say 23 degrees. Sorry, I'll try to remember to write bigger. This is what gives us seasons, of course. Like right here, it would be summer in the southern hemisphere and winter in the northern hemisphere. Right here, it is summer in the northern hemisphere and winter in the southern hemisphere. And the tilt doesn't change much from year to year. Like we are pretty firmly at 23 degrees all the time. And the reason for that is our enormously large in comparison to the size of our planet, moon. Like we've got a big old honking moon. It's not the biggest moon in the solar system, but it is by far the biggest moon in comparison to the size of the planet that is orbiting. And that really helps to fix our axial tilt. Other planets, not so fortunate. Mars only has 2 tiny weird moons, and Mars's orientation is shifted by a lot over time. So the Earth is like this. If you wait a few 10,000 years, it's going to go from being like this to moving around like this. Like the direction that the tilt is pointing will slowly change. It never points straight up. It always stays at 23 degrees relative to its orbit, but it does slowly precess and point different directions. Precessing being the fancy word for turning. So wait. $10,000 years or so. And instead of the Earth pointing that way, it will now point that way. This is why the North Star changes, because what star the Earth's North Pole is pointing at literally does change over time. And this is also why the zodiac is out of sync relative to what is written down as in your newspapers. So we want summer to be around August, and we want the Earth to be warm when that's the case. Warm up here, cold down here, right? And so the Earth is an entirely different seasonal state if the tilt is this way. Like in this part of the solar system, now it's summer in the northern hemisphere and winter in the southern hemisphere, whereas before it was winter in the northern hemisphere and summer in the southern hemisphere. But what part of the solar system it's in, and hence what stars you see when you look that way, very slowly shifts. But the zodiac has shifted by about 20 days relative to the astrologers, or maybe astronomers, that first invented the idea of it. Okay, back to the PowerPoint. Are you back to the PowerPoint? Or are you still looking at the chalkboard? I see somebody nodding. Thank you. All right. So most cultures have had a sense that the Earth was the center of the solar system, and the sun, the moon, the stars, and all of the planets orbit the Earth. In Western culture, this model of the solar system was first put forth about 3,000 years ago by some ancient Greek philosophers. And then it was clearly elucidated by the Greek astronomer Ptolemy around 100 to 170 Common Era. We don't know for sure exactly when. In the simplest version of this model, the sun, moon, stars, and planets all move in perfect circles around the Earth. But after watching the sky for kind of a while, there was something that could not be explained by the normal geocentric model. Planets generally move east to west across the background stars. Planet itself comes from a Greek term meaning wandering star. So every once in a while, planets do something weird. So here's all our background stars. Throw a little color in there because stars do have color. Oh, I apologize for that squeak. Let's see if the green chalk is as odious. So here's Mars, and here is east, and here's west. So day one, you wake up and you look at Mars, and it's here. Day two, it's here. Day three, it's here. Day four, it's here. This is normal and what you'd expect. But a few times a year, you see this. Day one, day two, day three, day four, day five. So it goes backwards relative to the background stars. And then it resumes its motion this way. So if everything's going around in a circle, you really can't explain that. So you have to change your model somehow in order to account for that. And when planets do that weird background motion thing, this is called being in retrograde. And now you know what retrograde means. And so when people say, oh, I'm having an off day, Mercury must be in retrograde, that means Mercury appears to be moving backwards relative to the way it normally does. And there in the background is Uranus doing its normal motion, as opposed to Mars, which is doing a little loop-to-loop where it briefly goes backwards. So the normal east-west motion is called prograde, and the backwards west-east motion is called retrograde. And if you want to keep a geocentric model, then one way you can account for this is by putting each of the planets on little spheres. And so the spheres turn as the main sphere that they're traveling on is turning, and this can lead to occasional backwards motion. Those little spheres are called epicycles. And look, if you have an epicycle, you can get that kind of backwards motion when the sphere itself is turning in such a way that it is approaching the object that it's orbiting. And if you watched over the course of a year, the epicycles would look something like this. Let me get to this YouTube video. Are y'all now looking at YouTube? Okay.
Yes.
So I'm going to play this video in extremely slow motion. So here is the sun and some planet that is moving on its epicycle, and it occasionally goes backwards. The sun doesn't need an epicycle because the sun never does this thing. It never seems to travel backwards relative to the way that it's supposed to be. Show you all that one more time. So it's turning towards, and as it's just passing the Earth at the center of everything, it goes briefly backwards and then it resumes its normal motion. And so that's how you can get retrograde motion if the Earth is the center of the universe. And then for planets outside of Earth's orbit, it's a little bit less contrived. So back here to the beginning. Ah, it's here for some weird reason. Hold on. All right, that's not what I want, but I'm just going to go with it because this is the next video. Actually, I'm not going to go with it because the sound quality is awful. I don't know what's going on with YouTube today, but if you
want to put it on mute?
What was that?
Would you want to put it on mute?
Sure, I'll just put it on mute. So this is an example of the movement of the planets if they're following their epicycles. And, you know, there used to be very pretty music associated with this, and they slowly add planets one at a time. All of the signs out there further away are the zodiac signs. And so you can see that the planets move through the zodiacs exactly as the sun moves through the zodiac. And then add more and more and more planets, more and more and more spheres. And then at some point, the video switches to what is real, which is that the Earth is going around the sun. And you get a different explanation as to what's going on with the epicycles. And seen from this perspective, the epicycles happen when the Earth is moving on the inside track and it laps the planet that it's going around. Okay. This particular lecture has a lot of switching around. So there is my Epicycles demo. Right now, this is, let's switch to the blue object, pretend that's the Earth. And then the sun is going around the Earth, that would be the yellow thing. And the red would be Mars or any other planet that you choose. And Mars is able to do this looping due to the presence of the epicycles, or at least that would be the explanation. Yes, question.
Why does it do like that little curve every once in a while? That's why.
Let's go back to it. I think I just closed the screen. Oh, this is not the one I wanted, but it will serve perfectly well. Oh, no, it will not. Hold on. Let's get the right applet. There we go. So the reason you get the little dippy loop-to-loops is that the planet is moving on a circle, here not shown, but I'll do another applet later that does show it. And that circle is largely going around the Earth. But then there's a second circle, which is turning as the big circle turns. So here we have the Earth. Here we've got Mars. And Mars, according to the geocentric model, is going on a big old long path around the Earth, but it's also got this little path here. And so the loopy circles happen because Mars is turning around on this circle as it moves around the Earth. Oops. And so if you follow this through, the turning on the epicycle will give you these little loop-to-loops. And every time you have a little loop-to-loop, you've got retrograde motion. And when it's going like this, it's prograde motion. I think I forgot to pin my chalkboard. Hold on. Everybody looking at the chalkboard now? So this is the prograde part. Every time it does a loop-to-loop is the retrograde part. Does that help you understand? Any follow-up questions?
That helps you understand.
Great. So for hundreds of years, most educated people believe the Ptolemaic model, that there is a geocentric solar system with epicycles. A few ancient Greek and medieval Arab astronomers had floated the idea of a heliocentric solar system. The idea did not become fully fleshed out until about 1500 Common Era. Nicholas Copernicus published a book on the revolutions of the heavenly spheres. I'm not going to butcher the actual title because my Latin is non-existent, in 1543. So his hypothesis was that maybe the sun's the center of the solar system. And he was quite clever in how he proposed this. He was actually commissioned by the Catholic Church, otherwise in Western Europe at that time known as the Church, the only one. Well, certainly the dominant one. And the Church wanted the calendar fixed because the calendar was sliding by their current way of keeping track of it. So they needed some modifications to it, and Copernicus said, hey, I'm not saying this is real, but what if we pretend the sun is the center of the solar system and the Earth is going around the sun and the other planets are going around the sun too? Could we then use this hypothetical situation to keep track of the motions of the planets and hence the motion of the Earth better and improve the calendar? So even though he was very careful in saying what he in making his point in a way that was diplomatic, he was still worried about backlash from the Church. And so he didn't publish until a year or so before his death of natural causes. And the Church more or less took it without any kind of problem. They were like, well, this fixes the calendar, so great. If you do have a sun-centered solar system, then you get a different reason for retrograde motion. And that would be this. For a superior planet, for a planet that's outside the orbit of Earth, as Earth moves on a smaller circle, and as Earth moves faster than every planet outside of it, it's going to frequently lap the planet, exactly like a race car passing another race car on the inner track. If the race car on the inner track is moving faster and the race car on the outer track is moving slower, this is now a perfect analogy. Like, this is exactly what it would look like. And here are the animations for Copernicus's model and what that would look like. So now we have a sun-centered solar system. This is an inferior planet that is passing the Earth. This inferior planet is not only moving faster than the Earth, but it also has less space to cover because the orbit is smaller. So yeah, occasionally it will just lap the Earth, and when it's lapping the Earth, it seems to go backwards. Let's see the key bit of this again. So it's coming up on the inside, and it passes us. And as it passes us, it briefly does some retrograde motion, and now it's back to prograde as usual. So that's for an inferior planet, or a planet inside of our orbit. This is for a superior planet, a planet outside our orbit. And in this case, the retrograde motion happens because the Earth is lapping the planet that is outside of our orbit. Which I guess it does right at the very beginning, because I missed it. Okay, the Earth is coming up on the inside, it's moving faster, it's moving faster, it's moving faster, it's passing. The planet's moving backwards in the sky relative to the way that it normally does. And now the Earth is way ahead in front, and the planet has resumed its normal motion. And so this is the way it really works. Like, it turns out, the Earth is not the center of the solar system. And so that is the correct cause of retrograde motion. And let me show you an animation of that if I can. I can just use this one. So all you got to do is put the sun back in the center of the solar system, and the blue planet is presumably Earth. The red planet is presumably Mars. And as the blue planet laps the red planet, you get retrograde motion. So prograde, 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 retrograde, prograde, 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 retrograde, so on and so forth. So challenge problem. Let's imagine that you have a bunch of marbles, all of them have a radius of about 10 centimeters. What is your mathematical estimation as to how many of them could fill a spherical container with a radius of 10,000 centimeters? I'm going to put a problem like this on some quiz someday. So let me give you a minute to work on it. I'll start writing it out on the board, but I won't spotlight the board yet. And better if you work on this yourself rather than keeping an eye on what I'm doing. Okay. Anybody want to share their answer? You feel pretty confident? That's totally fine. You don't have to. Yeah, Jaden, do you?
Let's see, from my math, it's 1,000 to 1.
Mm-hmm. Okay, so it's 1,000 to 1, but this is a volume problem. So three-dimensional space. So in order to figure out how many would fit, 1,000 times 1,000 times 1,000, which is 1 million. Excuse me, a billion.
Oh, okay. Let's interpret the thing.
Cool. Very good, y'all. Thanks for trying it. Let me unpin my chalkboard. So now we get a little gossipy. I hope you all enjoy some gossip. So this guy's name is Tycho Brahe, and he's a Danish astronomer. He's rich. He's a jerk. There's his house. He had his own private island that the king of Denmark gifted him. And he built an observatory there, and he kept really, really, really careful track of what's in the skies. And he was assuming not exactly a geocentric model. Well, it was a geocentric model, but it's a weird geocentric model. He thought maybe the moon goes around the Earth, and then the sun goes around the Earth, and all the other planets go around the sun. So closer to right, but also wrong. And he was keeping such careful astronomical observations because he wanted to prove this. Now, here's the thing about Tycho Brahe. He had really, really, really good eyesight and a super steady hand. His observations were incredibly good. So he was able to compile an enormous amount of information over the course of decades worth of observing. Died young, ate himself to death, and some part of his internal body burst and he died of sepsis. The story I've heard is that he was eating with the king, and it's rude to get up before the king gets up, and he just kept on eating and eating and eating until he'd had enough. Other stories about Tycho Brahe: he kept a pet dwarf, and here I mean a dwarf human, not like a chihuahua. And he would put this person on a leash and walk them around. He lost his nose in a sword fight in a duel when he was younger, and he'd walk around with either a silver replacement nose or a gold replacement nose, depending on his mood. And that's about all of the Tycho Brahe gossip I know. So his story is mainly interesting because of this man, Johannes Kepler. So Kepler was a student of Tycho Brahe's who inherited Tycho's data when he died. Now, he didn't get the data easily. Brahe's family fought really hard to keep him from getting it. And he was about as opposite from Tycho Brahe as you can imagine a person being. One of the main differences was that Kepler was extremely sickly. Like, he had horrible diseases when he was young, and he had terrible eyesight. Whether that eyesight was brought about by the many, many, many diseases that he had contracted as a child, or whether he just would have had bad eyesight no matter what, we don't know. But the important thing is that there's no way he could have made the kind of observations that Brahe made. He needed access to that data to figure out how the planets were actually moving across the sky. And he got it. And he went through a bunch of different theories about how the solar system might be constructed. He wondered if the planets might be moving along a path that was prescribed by Platonic Solids. There are only 5 objects in the universe that have equal sized sides. One of them being a four-sided figure. So triangle, triangle on the back, triangle on the back, triangle on the bottom. One of them being a six-sided figure. This would be your typical dice. And then you have an 8-sided figure, a 12-sided figure, and a 20-sided figure. And that's it. Those are all the ones you can make, at least according to mathematical proofs. And in this case, the mathematicians are right. Like, this is not that hard of a problem to work through. So we tried to make the planets move around some pattern that was related to this. He tried straight up circular, tried a bunch of different stuff, worked on it for decades. And the thing that he finally settled on is he tried to make the planets fit the shape of an ellipse. And that worked. He actually did the ellipse after several decades worth of trying at other things because he figured that somebody else must have tried an ellipse earlier. So it's not that. Hence all of the weird theories he cooked up along the ways. But once he realized that the planets were moving around the ellipse, he came up with a few laws that happened to be true. Kepler's first law: the sun is the center of the solar system, and the planets, including the Earth, are orbiting the sun. Now, when I say center of the solar system, I don't mean exact dead center. The thing about an ellipse is that it's got two foci associated with it. And the sun would be at one of them for every single planet. And if you have moons orbiting around a planet, then the planet would be at one of the foci of the ellipse, because moons move around the ellipses as well. If you want to make this for yourself, it's pretty easy. Take a push pin, take another push pin, put a piece of string around the push pins and pull it taut, and then just draw a circle holding the string as tight as possible. And that's how you make an ellipse. Ellipses come in all different shapes. A circle is technically an ellipse with both of the foci on top of each other. And so when I told you earlier that the Earth's orbit is nearly circular, that doesn't break Kepler's law at all. A circle can be an ellipse. And then ellipses get more and more and more stretched out. And the word for being stretched out is eccentricity in math talk. Sorry, keeping an eye on the time. In general, planets tend to have orbits that are extremely close to circular. Oh, sorry, let me spotlight this. So the two foci would be very close. This is typical of planets. This kind of orbit is more typical of comets. And we'll say that the sun's right here. So the most famous comet, Halley's Comet, takes, I don't remember the exact number, but something like 76 years to come back to being close enough to the sun that it's visible. And part of the reason that it takes so long is that most of its orbit is way out here, far away from the sun. And then in order for a comet to develop a tail and shine brightly enough to be seen in the night sky, it's got to be close to the sun because the sun literally makes comets evaporate. So the tail you see from a comet is caused by the sun heating up the comet, and the comets are made out of mostly ice, and that ice is just turning into glittery pieces and being blasted off the surface of the comet itself. So quick bit of vocabulary. When you think about what an ellipse is, there are two foci. And there's something called a semi-major axis and a semi-minor axis. For our purposes, the only thing that's really important here is the semi-major axis. And importantly, that is not from the long side to the foci. It is from this side all the way to the mathematical center, halfway in between the two foci. And I think when people try to think of what semi-major axis is, the main thing they're going to mess up is that they're going to go from the focus to the center or from the outside to the focus or something like that. But it's from the widest side, one corner of it, to the center. So all these shapes can be formed by taking a cone and cutting it into pieces. You've got a circle if you cut straight across. You've got an ellipse if you cut diagonal. You've got a parabola if you cut right through the middle. And you've got a hyperbola if you cut through the outside. Hyperbolic things enter the solar system and then they leave the solar system. So the weird asteroid-like object that just sailed through the solar system, which I believe is pronounced Omen. I'm not going to be able to say it. But anyway, that one would have been in a hyperbolic path around our sun. The sun did affect it, but not enough to make it go into orbit around it. So Earth's orbit is currently only very slightly eccentric. And other planets are much more eccentric. Excuse me, I shouldn't say other planets. Pluto, not in the club anymore. But they are largely circular. The minor planets are much more likely to have a very eccentric orbit. So Makemake, Eris, Pluto, so on and so forth, have pretty eccentric orbits. The major planets pretty close to circular. And of the major planets, the smallest one, Mercury, has the most eccentric orbit. It's actually more eccentric than Pluto is. Kepler's second law. If you take an imaginary line connecting a planet to the sun, and then you draw a new line after a period of time, the planet will sweep out equal areas in equal times, regardless of where the planet is in its orbit. Oh, have you guys been looking at the board the whole time? All right. I guess so. Well, back to the board. So the upshot of this law is that planets move a lot faster when they're closer to the sun. Let's take a totally imaginary planet. If you wait 15 years and it sweeps out this much area, then when the planet's much further away, exaggerate this a little bit, and you wait another 15 years, and the planet would have to be moving much faster here than it is when it's here. So the upshot of Kepler's second law is that planets move much faster as they get closer to the sun. This is also why Halley's Comet is spending so much time missing in action. The sun's here, the orbital path of a comet is like this. Not only is there far more of its orbit that is far away from the sun, but it's also moving a lot slower when it's out here. Back to the PowerPoint? I think so. So basically this law means that planets move faster in their orbits when they're close to the sun and slower when they are far away from the sun. And then there's a mathematical relationship that goes along with this. This would be Kepler's third law. But I'm not going to ask anybody to do that math. I'm just going to ask you to generally understand it. The closer you are to the body you're orbiting, the less time it takes you to orbit. All right, I got to check on the classroom next door. I hear some movement. I will be hopefully right back. Sorry about the delay, y'all. All right, so if you were to use this to do math, that A is 1 astronomical unit, which is the distance from the Earth to the sun. but we're not going to do that math. And if you go ahead and plot everything in the solar system, they all follow this law. Mercury, Venus, Earth, Mars, Ceres, which is the biggest planetoid in the asteroid belt, has about a quarter of the total mass of the asteroid belt right in itself, actually. Jupiter, Saturn, Uranus, Neptune, Pluto, and Eris all follow this law. Anything that orbits follows this law. The law is different for different solar systems, excuse me, for different star systems. Only our system is a solar system. And it would be different if it was moons orbiting around some other planet. But the basic law is followed. You just have to put in slightly different constants. Okay, so let's start synthesizing all this information. Suppose you read in a newspaper that a new planet has been found around another star. The newspaper states the average speed of the planet is 33 kilometers per second. When the planet is closest to the star, it moves at 31 kilometers per second. And when it is furthest from the star, it moves at 35 kilometers per second. I'm going to leave this up for long enough for the people that are actively in class to read it. If you feel like sending me what you think the answer is in chat, that would be great. Of course, people that are watching this video can just pause it. All right, I just read it twice, so hopefully that was enough. And the right answer is that Kepler's second law says the planet must move faster when it is closest, not furthest from the star. So something was wrong with that newspaper. Now we're going to do more synthesis. There we go. So the figure below shows several different positions of a comet traveling in an elliptical orbit around the sun. 4 different segments of its orbit and the corresponding triangular shaped area swept out by the comet have been shaded in gray. Assume each of the shaded triangular segments have the same area. So rank the time from greatest to least for the comet to move along each of the segments. And I'm going to give a little bit of time for the people in class to think about this. But the answer would be, if the areas are all the same, then it should take an equal amount of time to move through A, B, C, and D. And then the figure before shows 4 locations of an asteroid during its elliptical orbit around the sun. So rank the speed from fastest to slowest that the asteroid would have at each of the 4 marked locations. Give you all another 20 seconds or so to think about it. All right, D is fastest, C is second fastest, A is slower than C, and B would be the absolute slowest this asteroid is moving during its journey. All right, I fully admit this problem is weird. The way that you do it is you look at the semi-major axis. So the question is, what orbital period is the most to the least? And what you have to do to solve this problem is draw the orbits separate from each other and then mark the semi-major axis on each of them. So I will do that for you. And remember, how long a planet takes to go around the sun depends on what the semi-major axis is. And the semi-major axis is formally this part of the ellipse from the one side of the widest proportion to the center. So, all right, we've got a diagram that looks like this. we're going to take it apart. I'm going to mark the semi-major axis of this one, semi-major axis of this one, semi-major axis of this one, and the semi-major axis of this one. So in fact, C would take the longest to go around the sun, then E, then B, then D, then A. And I'm actually not going to do that one because I no longer go through this with that level of detail. So there was your Kepler's law practice. Challenge problem. I tend to repeat this problem a lot, which is why I'm having you practice it now. The Earth is 1 astronomical unit, or 8 light minutes away from the sun. Mars is 1.5 astronomical units, or 12 light minutes from the sun. What is the longest possible delay in communication between Mars and the Earth? What is the shortest possible delay? Show all your work and make a drawing for the best chance of partial credit, I say, because normally I'd walk around and grade these, but that's not happening this time. So go ahead and give it a shot. I'm gonna work it out on the board and then I'll spotlight the board after I've got it written down. Excuse me. So 8 light minutes and 12 light minutes. Back to the board. So slowest possible delay would be from here to here. 12 minus 8 is 4 right here. So a 4 light minute delay in between Earth and Mars as far as communication goes at the best. And at the worst, Mars would be all the way over here. And that would be 8 plus 12. And so you'd have a 20 light minute delay. At the worst. Or at the most, I suppose I should say, if you're not looking forward to making that call to your grandma on Mars, maybe 20 minutes is ideal. Another challenge problem. What time of day does a waning crescent moon rise? Do the drawing and work it out. Let me unspotlight the board and I will do this. But you should be doing it too. This is another problem that I tend to repeat over and over and over again, which is why I have y'all practice it so much. The sun is that way. Here's the Earth. Here's the orbital path of the moon. Almost everything in the solar system, well, yeah, almost everything in the solar system orbits counterclockwise as viewed from above, with above being what you see if you start at Earth's North Pole and just start to gently float upwards. So this would be a full moon. This would be a new moon. If it's full moon here and new moon here, and the moon's going around like this, then up here it's waning. Yet here it starts waxing again. And I want a waning crescent moon, so that would be round about here. So what time of day does it rise? The Earth itself is rotating around counterclockwise once every 24 hours. When it's midnight on the Earth, I'm definitely not seeing it. There's a whole planet in the way. But a little bit after midnight, the moon is going to creep up over the horizon. And then after noon, it's going to set below the horizon. So I'm going to say that this moon rises around 4 a.m. and sets around 4 p.m. And if you're not good on that still, it's an excellent idea to set up a Zoom appointment with me and have me go over it, because you know for sure some portion of your points in the class are going to rely on a problem like this at some point. More gossip about astronomers. This guy's name is Galileo Galilei. He was an Italian astronomer who lived from about the mid 15th century Common Era to about the mid 16th century Common Era. He was alive at the same time as Kepler. Kepler wrote him a few letters. Galileo never wrote back. He didn't actually design the first telescope. I need to go and fix that, but he vastly improved on the design. And with this telescope, he was the first person to observe sunspots, which, by the way, never point your telescope at the sun and look at it. Galileo died blind for a reason. But anyway, he looked at the sun and he saw little spots on the sun. He saw craters on the moon. He saw the moons of Jupiter, and may have been the first person to do so. Although remember, there was a Chinese astronomer who very plausibly put a very small stick in front of Jupiter and then saw the moons that way. Because Jupiter's moons are bright enough that you could see them with the naked eye, as long as Jupiter wasn't there. He was the first person to see the phases of Venus, and he was the first person to point his telescope at that blurry white portion of the sky that is brighter than other portions of the sky, and realized that it was full of stars, that all that light was coming from stars that were so tremendously far away that it's all blending together into just a brightening of the sky. So there's his observations on the moons of Jupiter. And the moons did follow Kepler's law. It had slightly different constants involved in it because these moons are orbiting Jupiter, not the sun. But once you account for that, they perfectly follow Kepler's laws. There's the Milky Way, just to remind you what Galileo pointed his telescope at. You can do the same thing. If you haul even binoculars out into a place that's dark enough that you can see the Milky Way, which is quite a journey in California, and you take the binoculars and you just point it at that whitest thing across the sky, you're going to see more stars than if you point it in some other random direction. You observe the phases of Venus. And there they are. And there's his drawing of them. And here's a modern picture of Venus's phases. The phases of Venus don't jive with the geocentric model. So if the Earth is the center of the solar system and Venus is on an epicycle, then we would never, ever, ever see Venus be full. We would only see it be new and have a little bit of a crescent and then a little bit more of a crescent, which is called a fat crescent, as opposed to this. Like clearly Venus does get full. And interestingly, when Venus is brightest in the sky, it is also furthest away from us. The sunlight being fully reflected on the surface of Venus makes Venus so bright that this, oh, excuse me, no. When Venus is brightest, it is closest to us and it's in crescent phase. I don't know what I was talking about for a second. So Venus is brightest when it's in crescent. When it's full, it's far enough away that that is actually less bright. So this is a major blow against the idea that the Earth is the center of the solar system. So try on your own, draw a picture of the heliocentric model in your notes. What possible phases can be observed of Venus in this model? I will help get you started. Of course, people following around at home are just going to rewind their video. But for those of you that are here in the class, for the heliocentric model, you'd have Earth here, the Sun up here, and then Venus would be on its own little epicycle here. And then the side of Venus facing the Sun is the side of the Venus that's illuminated, just like the Moon and everything else in the solar system. So go ahead, try to figure out those phases, then go back and see if you're right. And let me get an animation of the phases of Venus. Oh, okay, it is working. So here you go. Venus is now almost at its brightest. It'll be at its brightest about here when there's enough sunlight being reflected that it means something, but it's also very close to the Earth. Venus is so bright that when it is at its brightest, you can see it during the day. If you know just where to point your binoculars, you can see it. Oh, somebody asked midnight question mark, and I'm not sure how long ago they asked that. Oh, it was probably for this, which has been erased, for that rise and set thing. So I calculated, or I drew a picture, and I guessed that it rose about 4 a.m. and set around 4 p.m., I think. Do you want me to go over that again?
No, it's okay.
All right. Okay, so now we get to the gossipy part. Galileo was born pretty rich, and he actually grew up with a person who later became the Pope. So the Pope was his buddy. But here's the thing about popes. Popes die and get replaced. So eventually the Pope wasn't his buddy anymore. And everybody knew Galileo was an astronomer. Everybody knew that he was a proponent of the sun-centered solar system. This is a problem for the church, and it's not because of anything in the Bible. I think there's exactly one passage in the Bible that talks about the motion of things in the sky. And it's something like, somebody commands the heavens to stand still. And that's it. So the Bible is really moot on the whole, is the sun the center of the solar system, or is the Earth question? It just doesn't care to discuss it at all. The reason the Catholic Church doesn't like the idea of an Earth-centered solar system is that there's a lot the Bible doesn't talk about. Like, in order to construct a culture and a civilization, you kind of need a fleshed out philosophy of natural sciences and all kinds of other useful tools in your toolkit for communication and so on and so forth. And the person that the church ended up choosing to take this from was a guy named Aristotle. And the church adopted Aristotle pretty much in its entirety. So what Aristotle, who was a Greek, who was born about 400 years before Jesus was born, thought about the universe became what the Catholic Church thought about the universe. So the Catholic Church wasn't anti-Earth-centered or wasn't anti-sun-centered solar system because of anything in the Bible. It was because of stuff that Aristotle wrote down. Regardless, that was the church's position. The Earth is the center of the solar system, and Galileo was saying it wasn't for various reasons, the phases of Venus, so on and so forth. So the church calls him in, and he gets told, look, you can say whatever you want within limits as long as you pose these ideas as hypothetical ideas. So just say, consider the possibility. Don't say that this is true, because then you'll be coming into direct conflict with us, and we don't want that. So Galileo went away. He wrote a book called The Dialogue in Between Two Systems of Thought. There are 3 characters in the book, and if you take the translation of their name, one of them is named Smart, and one of them is named Stupid, and I don't remember what the third person's name was. He's basically just there to provide background dialogue. And Galileo, the person named Smart, explained his ideas about a sun-centered solar system, and he had the person named Stupid explain his ideas about an Earth-centered solar system. And another thing the person named Stupid did was that he had several direct quotes from the current Pope written as dialogue for him. So this wasn't a good idea. Here's a picture of the telescope used by Galileo for whatever reason, but that's almost the end of my Galileo. So I'll tell you how his story ends. He's called in front of the Inquisition. He's made to publicly recant the idea that the sun is the center of the solar system. He's put under house arrest, and he goes blind and he dies. Now, before you feel too sorry for him, keep in mind that he's a very rich person. Being under house arrest meant that he was basically living in the modern equivalent of a mansion. And he was also allowed to have visitors. And any number of famous and prominent scientists made the trek to Italy to come and visit him. And so he had a lot of interesting conversations in his later life. There's a model of the telescope Galileo used. All right. I want you to draw a picture of the Earth and the sun. And I'll draw a picture of the Earth and the sun too, to help you along. I actually need a picture of 3 things. I need a very distant star. I need the sun, and I need the Earth. So the Earth is orbiting counterclockwise, and it is spinning counterclockwise. So there's a bunch of different ways you can define a day. Here we want to consider 2 of them. A solar day is what you get if you stand in a field and you point at the sun, and then you wait with your arm up, pointing in the same direction until the sun comes back to the spot that you are pointing at. Then you say, that's a day. Another way to tell what a day is to point at an extremely distant object, like a star. So you pick a star in the night sky, you point at it, and then you stand there until the star comes back and your finger is directly pointing at it again. That too is a way to quantify a day. So which is longer, a sidereal day, which is what we call a day that's measured relative to the stars, or a solar day? I'd just like you to try to figure this out. For those of you who are here, I'm going to give you a minute to work on this because it's not trivial. but I think it can be understood through drawing a picture. And those of you at home can just pause.
Solar day?
Think a solar day is longer? Sounds reasonable, but it would also sound reasonable if a sidereal day was longer. So the Earth is turning, and the relevant thing in terms of determining whether a sidereal day or solar day is longer is that the Earth is also orbiting. And this orbit means nothing to this very distant star. Like the orbit of the Earth is infinitesimally small in comparison to the distance to even the closest stars. So when you're measuring a day against a very distant star, it doesn't matter if the Earth is here, or here, or here, or wherever in its orbit. Okay. That was a minute. And here's the answer. So that is a sidereal day. When you point straight up, oh, sorry, that's a solar day because you're pointing at the sun. I'm sorry. So a solar day is a little longer than a sidereal day because the Earth has to turn a little bit more in order to get the sun back into exactly the same position. Oh, okay. So here's where we talk about the calendar. And I'm actually going to let somebody else do most of the talking about the calendar because they do an excellent job explaining it. And if I try it myself, I'm going to be drawing a lot of pictures on the chalkboard. And as you've noticed, drawing pictures is not really the thing that I'm strongest at. So we're going to watch this video from about 6 minutes in to about 15 minutes and 30 seconds in. And then I will stop it and ask if there's any questions over it.
Sundial time. To explore deeper, we have to begin by asking, what's a day? I mean, obviously, it's just the time it takes the Earth to turn around once, right? But according to what? Everything else in space is moving in some way too. The universe doesn't include a convenient sheet of graph paper at absolute rest we can trace paths on. The best we can do on that front is to look at very, very far, far, far away stars. So far away, like distant features of the landscape out the window of a moving car, they barely move as Earth does. Now, to them, a meridian on Earth completes a trip around about once every 23.9 hours. This is called a sidereal day. Sidereal means pertaining to the stars. Even though the sidereal day seems pretty clear, it's not what our calendars and clocks are based on, because there's a nearer star whose position relative to us has a bigger effect on our lives: the sun. Looking down on the North Pole at Earth's counterclockwise spin, the Earth also moves counterclockwise around the sun. After a sidereal day, the Earth has moved a bit along its orbit, so some more rotation is required for the same meridian to point back towards the sun again. This longer definition of one rotation is what the modern calendar and clock is based on. It is called the solar day. But here's the thing. Exactly how long the Earth has to rotate to complete a solar day changes day to day. Our clocks are just based on the average amount of time this takes. So throughout the year, they fall ahead and behind the sun. This is a solograph, a picture of the sun's path across the sky every single day. If our clocks actually told us local apparent solar time, if you took a picture of the sky every day at noon, you should get a line of suns. But this is what really happens. Over the course of a year, it will appear as though your clock is running slow, and then fast, and then slow again, and then fast again. This problem was known since at least ancient times, even if its cause wasn't.
So in theory, during this class, you have learned a lesson that will enable you to figure out why this is happening. So think about what we studied today, think about the motion of planets in general and the Earth as well, and see if you can figure it out. Just pause this and give yourself a couple of minutes.
In order to reconcile the two, the equation of time was constructed. In this sense, equation means to reconcile. The equation of time was applied to what a clock said in order to compute the real time, the solar time a sundial would show. Now, some fancy clocks called equation clocks were made that would do this for you, but eventually we gave up. We gave up and just said, no, the real time isn't what the sun says, it's what our inventions say. Now, this transition was a big one. It was humanity growing up. It was like the first time you realize you're stronger than your parents. We realized our timepieces were more regular and turned our backs on the timepieces nature had. But what causes this disagreement in the first place? As it turns out, the answer revolves around revolving, the way the Earth revolves around the sun. If the equator faced the sun all the time and the Earth always orbited at the same speed, the subsolar point would just stay right there on the equator throughout the year, and the amount of extra time spent rotating the Earth needed to do to finish a solar day would always be the same. But those two things aren't the case. First of all, the Earth's orbit is slightly elliptical, so its speed varies throughout the year.
Right. Kepler's, you know, it's embarrassing, but I don't always get them straight. Kepler's second law is the relevant thing to think about for this.
When it's moving around the sun faster around the beginning of January, the amount of extra turning time needed to complete the solar day is longer than when it's further away from the sun and moving more slowly. There's more. Because the Earth is tilted, the subsolar point is dragged throughout the year in a circle around Earth that's not the equator, so it changes direction, moving northeast, then leveling out and going southeast, before leveling out and going northeast again. During times...
If you're not within that path that was just drawn, you never get to see the sun directly overhead. If you're right on the equator, you get to see the sun be directly overhead twice a year. As far north as the Tropic of Cancer, or at the Tropic of Cancer and at the Tropic of Capricorn, you see the sun go directly overhead just once a year, and then it starts to go back the other direction. So we are not far enough south to see the sun directly overhead ever. It's always in the southern part of the sky in this part of California. And as a matter of fact, it's always in the southern part of the sky in every part of California. The only bit of the United States that is close enough to the equator to have the sun go directly overhead is Hawaii.
Of the year when the subsolar point is being dragged by Earth's orbit mostly east, it gains against Earth's spin faster. More time is required for the day to finish. Now, by coincidence, we are alive at a time when both of these phenomena lengthen and shorten days at roughly the same time. So they add up, making September 18th almost a minute shorter than the longest day of the year, December 22nd. For Northern Hemispherians, December has the shortest periods of daylight, but the whole solar day, from sunrise to sunrise, is for everyone on Earth the longest of the year on December 22nd. People in the north just spend most of it in darkness. Earth's tilt doesn't just affect how long a day is, it also affects how long a year is. This is because the Earth's tilt is what causes the seasons. For the half of the Earth tilted towards the sun, the same amount of solar radiation is spread across less space than it is on the other half, so there's more heat energy laid down per area. This causes what we call summer and winter for the other half. The amount of time from one of these seasonal orientations of the Earth to its occurrence again is called a solar year, or a tropical year. It's a very useful way to define a year because it contains every single season exactly, since it's based on the very orientations that cause them. But the problem is this: the number of solar days that occur in a solar year is not a whole number. It's almost 365. But after that many solar days, about a quarter of a day more happens before the solar year starts again. This makes designing a calendar more like designing a calendar. If your calendar only ever has 365 days in a year, over time, those dates will drift from the seasonal positions they used to occur during. Unless, this extra quarter of a turn adds up to a full day after 4 years. See, March 1st is coming a day too soon now. So if we just delay March by adding an extra day at the end of February every 4 years, a leap day, we're back on track. Leap days do not add days to your life. You're still going to live the same number of them. They just change what we call them. But really, who cares about being 1 day earlier every 4 years? I mean, 1 day isn't much, you hardly notice it. But over time, well, if America's founders had declared not only independence from Britain, but also from leap days, and abolished them from happening, today, 240 years later, their calendar would be a full 2 months ahead of Earth's position, putting America's coldest winter days in April and its hottest summer days in October. Adding a day every 4 years is what the famous Julian Calendar does. Introduced in 46 BC by Julius Caesar, it was the de facto standardized Western calendar for a very long time, more than a millennium. But it's not perfect. Look closely. Leap days actually move the calendar just slightly too far each time, because I lied. 365 and a quarter solar days don't occur within 1 solar year. The real number is slightly less and fluctuates year to year based on long-term changes to Earth and the sun's movements, which means adding 1 day every 4 years is just a teensy-weensy too many. By 1582, Julian calendar dates were 10 days behind the seasons compared to where they used to be. Now, that's not bad, 10 days in more than a millennium and a half. But the Catholic Church cared, because they wanted Easter to occur exactly when it used to centuries ago. Astronomers at the time realized that if leap days pushed the calendar too far behind the seasons, we would just need to celebrate fewer of them to fix the problem. Specifically, we would need 3 fewer leap days every 4 centuries. The rule they wrote to achieve this stated that every 4 years would continue to be a leap year, except if it was divisible by 100, unless it was also evenly divisible by 400. This removes 3 every 400 years. On October 4th, Pope Gregory XIII introduced this new calendar. It took his name, the Gregorian calendar. He also undid the drift that had occurred since the early days of the Julian and declared on October 4th that tomorrow would be October 15th. October 5th to the 14th never happened in 1582 in countries that listened to the Pope. It took the rest of the world centuries to hop on board. England and its colonies, like the soon-to-be United States of America, adopted the Gregorian in September of 1752, by which point their Julian dates were off from the seasons by 11 days, hence the disappearing of the 3rd through 13th. When adopted, the first of the year was also moved from March to January 1st. This explains why George Washington's birthday has 2 answers. Although more closely hitched to the seasons than the Julian, the Gregorian calendar still isn't perfect. Its difference causes dates to become 1 day off from the seasons every 3,216 years. Other calendars have been proposed, like the one Stand Up Maths calculated that drifts off even more slowly. His video is a great watch, by the way. But enough of all of this. Let's sit back and enjoy Earth's movement without trying to divide it up and name it. As a caveat, keep in mind that Earth's oceans and liquid insides and other celestial bodies are always pulling and tugging and sloshing around, minutely changing Earth's movements. Their effect is measurable, but difficult to notice at big scales and also don't look like much in the short term. Short, like the length of a human life. Looking from above the North Pole, the equator spins counterclockwise at about 1670 kilometers per hour. Relative to the sun, Earth orbits counterclockwise at 108,000 kilometers per hour, along a path tilted 23.4 degrees to its spin. Within our local neighborhood of stars, our entire solar system is drifting 70,000 kilometers per hour, roughly in the direction of the bright star Vega in the constellation of Lyra. And our solar system is part of a giant galaxy called the Milky Way, on a plane tilted about 60 degrees, approximately like the windshield of a car, looking from above Earth's North Pole. Our entire solar system races clockwise around the galactic center at about 792,000 kilometers per hour. Our whole galaxy is also moving through the universe. We know this because when the universe was very young, it was so hot, electrons and protons jumped around, and photons of light scattered constantly. They couldn't travel very far before scattering again, so the universe was opaque. But then, around 380,000 years after the Big Bang, the universe cooled just enough for electrons and protons to form hydrogen. Suddenly, abruptly, photons decoupled from this obstacle course and could travel relatively unencumbered. The universe became transparent to light. Since that moment, those early photons have been propagating through space. Every day, ancient photons that last scattered off this opaque fog at the moment of decoupling, a light day further from where Earth currently is, reach us. They are part of the cosmic microwave background radiation. It is visible in every direction. Microwave because although they used to be more energetic, the universe's expansion has redshifted them. Now, some parts of this radiation are more redshifted than others because of our own movement through the universe. Controlling for the movement we've already talked about, relative to this infinite, cooling baby picture of the universe, the first and oldest detectable light, we are headed, riding along in the Milky Way, in the direction that the constellations of Leo and Virgo are to us, at a speed of 2.1 million kilometers per hour, towards a thing we don't fully understand yet, simply called the Great Attractor. This is how you, on Earth's surface, are moving through the universe aboard Spaceship Earth. Okay, now stop. This is roughly 100 years of Earth's movement through space. This path we trace, from where we began here, is the path you will take through the universe in your lifetime.
Dun, dun, dun. All right. Any questions over anything that came up in that video?
Not really.
Okay.
Very interesting. I like this guy.
Yeah, Vsauce makes a lot of really good videos. I don't think you'll see him again in this class, but his YouTube channel is definitely worth a watch. Just See if he has a video on a topic that intrigues you. He's pretty good at laying things out carefully and in an interesting way. All right. So planets orbit the sun in ellipses. Planets move faster when they're close to the sun, slower when they're further away. And planets that are further away from the sun have longer orbital periods. But we didn't know what causes the planets to orbit. And the answer is gravity. And that's going to come from this guy, Isaac Newton. Last gossip about scientists this class. We're almost done. But I have some pretty juicy gossip on Newton. As much as he revolutionized science, he was not that into it. For every book he wrote on science, he wrote about 10 other books on alchemy. Did a lot of fiddling around with mercury, which is probably gave him brain damage. He was a little loopy by the end of his life. He was notoriously bad-tempered, and he feuded publicly with other scientists, something he was in a very good position to do after he got elected to some important positions in British academia. And this next class is going to be kind of an exploration of this, but let's set out his laws of motion. First law, an object at rest stays at rest. An object in motion stays in motion unless acted upon by an outside force. What that means for planets is there's got to be some kind of force on them. If there's no force, instead of going around the sun like this, force suddenly vanishes, the Earth is just gonna take a hiatus. It would go in a straight line ever after until some other force gets acting on it. And so there must be a force, and we call that force gravity. Or actually, Newton called it the Holy Spirit force, but nowadays we call it gravity. We don't see this force in action very much on the Earth because our world is just full of friction. It's hard to believe in Newton's first law because things grind to a halt, right? If I roll a ball across the floor, it's going to stop rolling relatively quickly. But we can approximate low friction environments by floating things on air or by using ice or something like that. And then you see Newton's first law obeyed much more exactly. Second law of motion, the harder you push on something, the faster it accelerates. And acceleration is just a measure of how quickly things speed up. And you know what acceleration is, because when you press on your car's gas pedal, you accelerate. If you want to move at a constant velocity, you eventually have to let up on the gas pedal. And when you slam on the brakes, you decelerate. And Newton's third law, forces come in pairs. Whenever you push on something, it pushes back with equal strength in the opposite direction. And I learned that law as for every action, there's an equal and opposite reaction. This is obviously a much more easily understandable way of phrasing it, but you too may have heard it taught to you in that way. I don't know. Do schools still teach you for every action there's an equal and opposite reaction? You'll have to let me know in class next week. Unless anybody here wants to chime in.
Last time I checked, they did. But
Okay. Well, it's a weird way of putting it because you have to understand that the word action in this context means force. So not very many people think of the word action as being equivalent to force. All right, final challenge for problem. What phase must the moon be in order to create a solar eclipse, and why? And a solar eclipse is when you can't see the sun. So pause this video, think about it. I'll give the people that are here live 20 seconds or so to chew it over. Okay, anybody want to tell me what the answer is? That's all right. You don't have to. All right. Here's the sun. Here's the earth. If I want to not see the sun, I need the moon to physically block it. And what phase is the moon in when it's right there? Well, the side that's facing the sun is illuminated. The side that's facing us is not. And the moon is new. And that was it, y'all. Unit 3 is done. Any questions over any of it from those of you who are in attendance?
I don't have any.
Okay, well, I'm going to let Napa process this video. And as soon as they're done with it and I can download it, I'll throw it up on YouTube and send the link to everybody in class. Have a great week. Ciao.
You too.